We're going to use this little shaker made from a couple Petri dishes with a little divider in between right here, and 10 heavier weight beads in white and 10 lightweight beads in orange to show how isotopes can be used to track climate change. Okay, so to do this, what we're going to have here is we're going to lay this down like this, okay, and the beads here represent molecules, and the orange lighter beads represent molecules that are comprised of lightweight isotopes, and the white beads represent molecules which have a certain amount of heavier isotopes, have a few extra neutrons. Okay, and if these are water molecules, this left side here could represent liquid water phase in the ocean, and this side here will represent water in the gas phase, say water vapor that is evaporated out of the ocean. And if I take this container and lay it flat on the ground and I shake it rather gently, we can see that the lightweight beads have jumped over the barrier a little bit more easily than the heavyweight beads. If we look at the water vapor coming off of the ocean, we find that the water that evaporates out of the ocean is a little bit more enriched in the lightweight isotopes than the heavyweight isotopes, especially when the climate is cool. Okay, climate is cool. It's harder for the molecules to get up into the gas phase, and the molecules that do tend to get into the gas phase tend to favor a little bit the lighter isotopes, the lighter water molecules. Now, this bead demonstration greatly exaggerates this amount of isotopic enrichment. Okay, but this effect does happen. Now, let's tip everything back into the liquid phase. And now what I'm going to do is show what happens when the climate is warm. When the climate is warm, we can get a lot more heavier weight isotopes into the gas phase. In this particular run, actually we had more heavy isotopes than light isotopes. It doesn't have to be that way. If it's shaken hard enough and long enough, you would find that statistically there'd be about pretty much an equal distribution of beads on either side, heavy and light. But I think this does illustrate that the harder shaking, which is representative of a warmer climate, does enable more heavy beads, which represent more heavy isotopes, getting up into the gas phase. Okay? And so how can we actually track these isotopes that have gotten up into the gas phase over the years and track the climate? Well, one approach we can do is we can look at ice cores inland from the oceans, because the water that gets into ice sheets from which ice cores are extracted have ultimately come from the oceans. And what we find is that when we sample the layers in the ice cores from these ice sheets, we find that during cooler time periods, there's a little bit more enrichment in light isotopes, and during warmer climate times, there's a bit less enrichment in light isotopes. And as I said, the changes are pretty subtle in real-world measurements, but they have been able to look back at climate variations going back hundreds of thousands of years by looking at ice cores and looking at isotopic effects.